Use this formula to determine the accuracy of the transmitter. We've applied the formula and determined that accuracy is 0.625%. This transmitter does not meet manufacturer's specifications. The zero is adjusted at the lowest point in the instrument's range by turning the zero adjust screw until the output reading here is correct. Since zero and span often affect one another, we should verify the span. These readings indicate that the transmitter's span does not need adjustment. Now, to conclude the calibration, recheck the upscale and downscale readings to ensure that the instrument is properly calibrated. We've seen that to calibrate a magnetic flow meter, you not only must use the appropriate test equipment, but also properly set the magnetic flow meter calibrator. On a magnetic flow meter calibrator, you can set the input signal, maximum output signal, and the test points used in calibration. In the next segment, we'll look at another type of flow meter and the procedure for calibrating it. But for now, stop the tape to review what you've seen. A vortex shedding flow meter can also be used to measure fluid flow. In this segment, we'll see how to calibrate this instrument. It requires a special input standard. But first, let's look a little more closely at how a vortex shedding flow meter works. The vortex shedding flow meter has three basic parts: the bluff body, a sensor, and a transmitter. In the process line, flowing fluid strikes the bluff body, and vortices are shed alternately on each side of the bluff body. The velocity of the flow determines the frequency at which the vortices are shed. The shedding of the vortices induces a resonance in the bluff body that is detected by the sensor. The sensor then converts the energy created by the vortices into electrical pulses. These pulses are conditioned and sent to the transmitter, which then sends an appropriate output to the next instrument in the loop. In order to calibrate this transmitter, we need an input standard which can simulate the electrical pulses counted by the transmitter. This is the calibration setup for a vortex shedding flow meter. A frequency generator is the input standard for this transmitter. The frequency generator has some functional features you'll need to see before you can calibrate the transmitter. Many of the settings on this generator are used to condition the electrical pulses sent to the transmitter. Now let's take a look at some. These switches select the output frequency. The attenuator, sometimes called the 0 to 30 decibel switch, is used to adjust the amplitude of the output signal. The amplitude control manipulates the output signal. The output signal can be attenuated by minus 60 decibels using this switch together with the 0 to 30 decibel switch. The protective ground or binding post provides a connection point for the instrument to earth ground. Remember, to maintain safety, always follow the manufacturer's instructions or your facility guidelines. When power is on, this indicator is illuminated. The manufacturer's instructions for a specific frequency generator will explain its special features in greater detail. Now that we've seen the input standard for this setup, what about the output standard? Here, a milliammeter will display the output signal. Before the connections can be made, the vortex shedding frequency must be determined. The vortex shedding frequency is usually provided by the manufacturer. However, you may have to calculate the frequencies yourself. The vortex shedding frequency is represented in pulses per second, or PPS. Pulse per second represents the alternate shedding of vortices on either side of the bluff body. This formula is used to determine the vortex shedding frequency. Now let's apply some values to it. RF stands for reference factor. The RF can be found on the transmitter's data plate. The RF is represented in pulses per US gallon. Here, 10.8 is the RF. The CF, or conversion factor, is a number that comes from the conversion factor table found in the manufacturer's instructions. The CF converts the RF to actual volume or mass flow rate units. Let's apply a conversion factor of 1 to this example. URV is the upper range value in US gallons per minute. We can use a URV of 2,250 GPM here. And time is a value that depends on the increment of time in which flow is measured. A value of 1 represents 1 unit per second, so a value of 60 represents 1 unit per minute, and a value of 3,600 represents 1 unit per hour. Now we'll apply 60 as the time value in this calculation. Working through the calculations, we find the vortex shedding frequency, or PPS, is 405 PPS for this example. We'll use this value along with a table provided by the manufacturer to determine the calibration settings. Span jumpers are required to calibrate this transmitter. They're used to define the application range for the vortex shedding flow meter test. The manufacturer's instructions provide the appropriate settings for the coarse span jumpers. The coarse span calibration prepares the instrument for the final fine calibration adjustment. The middle column of the coarse span jumper table lists the ranges of PPS frequencies at the upper range value. This line in the table indicates the setting for the coarse span jumpers at a vortex shedding frequency of 405 PPS. Here we can see the coarse span jumpers at the appropriate setting for 405 PPS. The medium span jumpers are set using another jumper table in the manufacturer's instructions. Once the PPS has been determined and span jumpers set in their proper positions, the frequency generator can be connected to the input terminals of the transmitter. The output side of the calibration loop is connected in series. After all the connections are made, set the fine span. To set the fine span, the frequency generator is set to the upper range value of the transmitter. Adjust the fine span screw until 100% output is indicated on the milliammeter. Once the fine span adjustment has been completed, as indicated by a 20 milliamp reading on the output standard, the zero can be adjusted. Precautions should be taken to ensure that no stray pulses affect the zero adjustment. Here we've disconnected the frequency generator and the signal lead has been connected to the shield of the coaxial cable. Zero is adjusted at the low range value, so the generator must be set to the appropriate setting following the fine span adjustment. The zero is adjusted until the output signal matches the input signal at the lowest input value. Again, since zero and span often interact, the span should be verified to make sure it's properly adjusted. As with other instrument calibrations, the span and zero should be adjusted and readjusted until both are correct. And as in the other instrument calibrations, a 5-point check will verify the instrument's accuracy. We've seen how to calibrate a vortex shedding flow meter. Appropriate input and output standards are chosen to simulate the process signal input and output. And the manufacturer's instructions are used to properly set the input standard so that adjustments can be made to the instrument. Stop the tape now and review what you've seen in this segment. It's sometimes necessary to measure mass flow for precise measurement requirements. A mass flow meter measures flow rate in weight per unit time rather than volume. This measurement is independent of temperature and pressure. Other flow meters which use volumetric measurements can be affected by changes in pressure or temperature. When the flow through a mass flow meter is increased, the output also increases, and when flow is decreased, the output decreases. In this program, we've chosen to calibrate a smart mass flow meter. Just like other calibration procedures, an input and output standard are required. However, because smart mass flow meters are digital instruments, they require a special communication device. This device or interface is required for configuration and calibration. The interface must be connected to the transmitter. It can be connected at any point in the loop as long as it's in parallel with the signal lines. Values can be input into the interface and downloaded to the flow meter. Before we configure the smart mass flow meter, let's take a closer look at the interface device. The configuration information is displayed on a liquid crystal. The top two lines of the LCD display user prompts and the values entered by the user. The bottom two lines of the LCD display labels for the function keys, F1 through F4. The bottom two lines can also display a current list of choices available to the user. When the device is turned on, a self-diagnostic program is initiated. This ensures that the interface is operating and communicating properly with the transmitter. The process variable key is pressed to display up-to-date readings from the transmitter. Pressing Help will display an explanation of the current display and the function keys. Restart initiates communication with the smart transmitter while the interface is turned on. Pressing the previous function key returns you to the last decision level to choose a different key function. And the alphanumeric keys are used to enter information into the interface. Pressing one of these keys will enter the numeric value of that key, and pressing the Shift key and then an alphanumeric key will enter an alphabetic value. In addition to the external features of the device, there are several internal memory components. They are safe memory, work registers, offline memory, and transmitter memory. The safe memory location is where existing transmitter information parameters are saved upon startup. It's called safe memory because it's non-volatile. That is, the data remains in memory after the device is turned off. The work registers are the actual location in memory where the data is stored. This memory location stores configuration information that was previously entered into the interface for downloading to a transmitter. The offline memory is non-volatile. The transmitter memory stores the data that's downloaded from the interface to the transmitter. This data is never accessed directly. It must be uploaded to the work registers first. Now that we understand more about the interface device, let's see how it's used to configure the transmitter. Configuration defines the parameters of the transmitter's operation. When the interface device is turned on, a self-diagnostic program checks to ensure the device is working properly. Pressing the Config key will begin configuration. Then enter information to identify the instrument. The parameters are checked and displayed by the interface device. You can then make changes or proceed with the configuration. Let's look at an example. In this case, the new range for this instrument is 0 to 500 pounds per hour. The low range value displayed here is correct, so Enter is pressed to proceed. However, now the upper range value that's displayed is inappropriate. It should be 500 pounds per hour. To change this value, you'd press the function key for change and then enter the new value using the appropriate alphanumeric keys. Now the specific information for the instrument in the loop is displayed. At this point, you can change the date to document the configuration. Once you've made any changes, press the key to download the data to the transmitter. Other operating parameters can be adjusted in the same manner. Again, you'll enter the data using the appropriate function and alphanumeric keys and then download it to the transmitter. Once the configuration is complete, the zero and span should be verified. To establish the zero and span values, the flow tube must be full of process liquid with no flow. Because actual process fluid is used, this procedure is typically done on an installed transmitter. To begin, Format is pressed, followed by the Proceed key. To establish zero, simply press the Auto Zero key. The Auto Zero automatically establishes zero to the properties of the process fluid. The resulting display will indicate that the mass flow meter is properly calibrated. Once you understand how the interface device works, calibrating a smart mass flow meter is easy. Since process fluid is necessary to the calibration procedure, this instrument is usually field calibrated. Mass flow meters are versatile instruments, and for this reason they're used to measure many different process fluids. Smart mass flow meters make changes like modifying the instrument range simple and convenient. In the next segment, we'll begin looking at instruments that measure level and their calibration. But for now, stop the tape and review what you've seen here. Level sensing and measurement provides information to help prevent the hazards of overflow and starving of process vessels. A level sensing device locates the interface between a liquid and a vapor, or between two liquids. Then it transmits a signal representing this value to process measurement and control instruments. Let's look at an example to see how a level sensor functions in a typical system. Here, the liquid in the tank is at its minimum level. The corresponding output, 4 milliamps, is also at the lowest range value of the milliamp meter. As the level in the tank increases, so too does the milliamp meter reading. When the liquid in the tank is at its maximum level, the milliamp meter reading is at the highest point in the range, 20 milliamps. If the liquid in the tank decreases to this level, the milliamp meter reading changes appropriately. As you can see, the level in the tank and the output signal are directly related. As one increases, the output signal changes correspondingly. One way that level can be measured is inferentially, using